Hello everyone, thank you very much for joining the lesson number 2. So today, like I promised, we'll talk about ACI topologies. ACI topology. On the very first day, on the day one, we talk more about what the use case of ACI is and why we need it. So today we're going to talk about the topologies supported for ACI. So we're not going to talk about any hardware or specifics about the programming. For this video, I want to just show you the design, the valid designs for ACI. So let's go. Let me get my a little bigger here. So ACI, when we talk about ACI design, we need to know about what is called class. Now ACI is based on a class design. Now what is a class design? Class is, it's a design that was formalized by an engineer called Charles Claus. He used to work for Bell Laboratories, and way back in 1950s, 1952, this gentleman came with an idea of creating what is called non-blocking switching network. And this design was, you have a switch 1, switch 2, and switch 3, right? And the best design for achieving a non-blocking switching design was to have, switch 4, switch 5, switch 6, and switch 7. So this design was to have these multiple layers of switches and have them connected in a full mesh approach, right? So you may have your way out and you have this full mesh approach of designing your network. Meaning whenever you have a failure, that failure is going to be isolated and contained and is not going to necessarily impact the entire design. So this way of designing network to achieve the non-blocking switching network was formalized as class design in honor to Charles Claus, the guy who used to work for Bell Labs way back in 1952. Now, take into account this design, multiple ACI's valid deployments, right? ACI valid deployments were created. So in a nutshell, we have 6 valid designs. 6 valid designs, but in one of them there is a small variation, but let's talk about those 6. The very first one is what we call standard. This is the standard, what you're mostly going to see. The second valid design is what we call stretch design. We have multi-pod. We have multi-site. We have again multi-tier. And the last one is called remote leaf. So these are the 6 main primary designs of ACI. Now let's talk about each of them and what are some of the requirements for each of these valid designs. The very first one The very first one, standard. On the standard design, this is a design where we have a max of 2 rows of switches. We have a row that we call spine, and we have a row that we call leaf. So 2 rows of switches, spine and leaves. We may have multiple spine, and we may have multiple leaves as well. But the important here is we only have 2 rows. Now, these rows, we have some requirements. One of the requirements, spine cannot connect physically to any spine. Likewise, leaf cannot connect to any leaf. So no cabling between spine and no cabling between leaves. What I mean by that is the cabling between spine and leaf, the cabling needs to be spine connects to leaf, and likewise in a cross connect. Spine can only connect to leaves, and likewise leaves can only connect to spine. That is the first requirement. This one is not necessarily a requirement, but a best is connection between spine and leaf to be 40 Gbps. I recommend it, but if we set a less amount of connection, like 10 gigs, 10 Gbps, is not going to necessarily impact the design. Now, when we have this type of design, as we talk about in the first day, that the main component of an ACI design is called APIC. Right? It's called APIC. And this design, the standard design, requires at least 3 APICs. And when we talk about, on the next video, we'll talk about some of the APICs design and why we need 3. But on this standard design, we need APIC interconnecting to leaves, but we need a third leaf connecting to APIC number 3. And just like in the initial conversation there, let me just get these 40 gigs. That was just informational sake. Now what we also need is this spine to also connect to that other leaf. Make sense? Now we have some leaf redundancy, and we have the APIC 3 that is connected on the leaf number 3. Now, this spine has some names and roles and responsibility. Spine, let me put here details. Spine is what we call intermediary device. Intermediary device. And just like we talk about, 2 connects to leaf. Connects to leaf. Now, also runs some control plane protocols. Those control planes protocols, what are they? So the spine is among other things that it does is running ISIS, intermediate system routing protocol for routing information exchange between leaf and spine. It also runs COOP, Council of Oracle Protocol, to allow for endpoint lookup services. It runs multi-protocol BGP for route reflection and transit routing. So all the interfaces on the spines, besides the management, it's called fabric port. Now let's talk about leaf details. Leaf. One, it's called access device, meaning the leaf switches, these are going to be the switches connecting to endpoints, connecting to servers, connecting to routers, switches, etc. But this is the access switches, access layer switch. So it allows for devices or endpoints to come in and to leave the network. Two, connects to spine. So leaf in a standard design can only connect to a spine switch. Now, why I'm putting this question mark? Because as we will see, the design number 6, which is a multi-tier breaks this rule by allowing spines to connect to spines for expansion of the data center. But forget about that design for now. We're talking about the standard design. On the standard design, we can only have 2 rows of switches. One is the row of spine, the other one is the leaf. Leaf cannot connect to leaf. Spine cannot connect to spine. Leaves, they need to full mesh connect to every other spine. And between spines and leaf, we run some control plane protocols such as COOP, multi-protocol BGP, we run ISIS. Okay. Now the leaf is also what we call VTEP for the VXLAN encapsulations and decapsulation. Four, on the spine, we can extend one of the switches with using FEX. Now, don't confuse FEX with a leaf. FEX is just a remote line card for a particular switch. So we're just adding more ports of a switch by adding FEXs, but it's not an independent switch. Meaning what? If I have a spine, if I have my spine and I have my leaf, I can come on the leaves and attach my FEX, making the leaf more, giving the leaf more port counts. But this one, I'm not really adding any more row per se. The reality is now that this leaf, so this is the practical design. The reality is that we have a leaf, and this leaf we're gonna dual home to a FEX. That's from a physical standpoint, but from a logical standpoint, we're not adding any row, right? We just extending the port counts on the leaf. Okay. Now, continuing with the conversation here, we again don't lose track of what we're talking about. Continuing with the conversation here on the standard design of ACI deployment, we have two rows: spine row, switch row. We connect these between each other, but these leaf, they do have several roles of leaf. Now, these roll of leaf, again, we have typically on the standard design, we have 4 roles. There is a 5th role that comes when we talk about a different design. There is another row that we add, but again, for the standard design, we only have 4 roles a leaf can take. One is what we call border leaf. Border leaf is when we're connecting these leaves, when we're connecting a leaf or multiple leaves to external network, either OSPF, BGP, ERGRP, static route, and we name it. When we're connecting it to an external network. The second role of a leaf is what we call service leaf. Service leaf is when the leaf is connecting to, let's say, firewalls, load balancer. So when we're connecting to layer 4 to layer 7 services, we call these a service leaf. The third one is what we call compute leaf. When we are attaching the leaf to a server, to a computing environment. And the fourth is what we call IP storage leaf. Again, when we are connecting directly to the leaf an IP storage device. So what are we talking so far? For the standard ACI deployment. Why is it standard? Because we can say it's standard because it is mostly what we're gonna see every single day. So these are the standard deployment. Standard deployment talks about we need to have spine, and the amount of spines we can have, it depends. We'll talk about that in just a second. What else can we have? Now we have the leaf. leaf 102, leaf 103, leaf 104. Just like I mentioned, in the standard design, the most that we can have is 2 rows. So we are done there. What we need to do now is physically cabling each leaf to, to one or multiple spines. We can have this design as well. So let's have our connection. Right? Now we have our connection like that. On the on these design, we also talk about we can also have our fexes. So let me extend the port count of leaf 102 and leaf 103 with fexes. But the fexes, they cannot dual home to separate parent. So they need to connect to the same parent. We can do that. Become now one of the critical components for ACI is your APIC. So APIC 1, APIC 2, and APIC, like I talked in the first video, that's the brain of the network. And we also need APIC 3. Right? APIC, they need to connect to these leaves in a, let's say, port channel config, a bundle config. Likewise, APIC 3 needs to connect to this bundle. So now we have multiple paths and redundancy. We talk about roles. These leaves, these are access. Between leaves and spine, we have multi-protocol BGP. We have COOP. We have ISIS. We talk about roles of the leaf. So this role of the leaf, this one can be a border leaf. Connected to a ISR. We can have service leaf connected to an ASA or a F5 load balancer. We can have our UCS 5108 connected, not there, connected to, let's see, my UCS 5108 connected to my FIB, FIA, right? Now, if we do that way, that becomes a compute leaf. Likewise, we may have our storage. Well, storage, IP storage. We can have our primary path going this way and secondary path going this way. Last but not least, in a typical, these standard design, we can have a max of 500 leaves. We cannot have more than 500 leaves on the standard design. Okay, that is a standard deployment of ACI, and we can say that yes, you may see that a lot. You may see that a lot. Now, suppose, right? Suppose now you have, this is your site 1. And this is your site number 2. I'm talking about physically, right? Physical, you have physically 2 separate sites. You have your spine 201, your spine 202, and your leaf 101 and leaf 102. But on this other site, on this other location, is a new data center or new physical data center, you also want to deploy your ACI. What you can do is deploy your spine 203, spine 204, leaf 103, leaf 104, and do your full mesh connectivity. Now, where are you going to place your APIC? Your APIC, you're going to have your APIC 1, APIC 2, same design we did on a standard design, but now this APIC 3 goes on this other site. Right? This is where you deploy the APIC 3. But the question now is, how do we interconnect these 2 deployments? Right? How do we interconnect these 2 deployments? What we can do is, you see these leaf 103, we can also connect, let me get it in red so we can see. We can connect the leaf 102 to spine 103. Likewise, right? Likewise, we can connect this leaf 103 additionally to these other spine. But you see, important takeaway here is we have almost the same standard design, but across 2 geographical locations. We are stretching the design. And this is the second deployment type, called stretch. Stretch ACI deployment. And what makes this design a stretch design deployment is what? Is the use of a new role that is called transit leaf. You see, transit leaf, I'm in blue. This is a new role that we adding on the ACI design on top of the standard, on top of those 4 initial roles. Now we having a new role called transit leaf, And we need at least one transit leaf in each location. And this transit leaf is going to be utilized to connect to the spine on the other side. As you can imagine, this one is across a layer 2. So we can use a layer 2 MPLS pseudo wire. But the point is, when we look at the leaf 103, leaf 103 is going to believe it's directly connected to spine 202 using the layer 2 connectivity. Requirement: between site 1 and site 2, we can have max 800 kilometers. This is roughly 500 miles. Very useful for migrations of data center. So you have your data center, you have your standard design on a data center, and then you move, and now you decide, okay, we are migrating data center to a new location. What are you going to do? Well, we can get one of those APICs in the data center 1, move it to a data center 2, deploy a new spine and leaf on the data center 2, and create and make sure we have at least one transit leaf on the data center 2, and use the layer 2 connectivity to connect respectively in a cross manner fashion. These are the second design deployment called stretched ACI design. So these are two basics designs. We talk about 6 variations. I will break this video for now, not to make it too large. And when we come back, we'll continue with the other 4 design architecture for ACI. So from now, you're walking away with a couple things. First, ACI design is based on a class architecture. And that is a theory to achieve a non-blocking switching. In a standard design, we may have at the most 2 rows of switches. One is spine, the other one is leaf. We talk about the protocols between spines and leaf. All the ports on the spines are called fabric ports. Right? And some of the expectations around spines and leaf. So I will break it for now. When we jump on the next video, I will do a quick recap before we go directly into the other designs, mainly multi-pod, multi-site, multi-tier, and remote leaf architecture. And by the way, when we talk about multi-pod, we have also a small variation called V-pod. Right? That is quite interesting. Without further ado, without much more, that's enough for now. And come back and join me on my video number 2 of ACI deployment. Have yourself a wonderful day, and I'll see you on my next video.